Hey, this is Lab Group 2A. My name is David Montgomery and I was the experimenter for this lab, which is number 11 on properties of liquid crystals. Basically, we worked on two setups. This is the first one that takes advantage of the Axometrix polarimeter. Basically, we have a function generator that drives the liquid crystal. There were two types. One was just a block attached to a mount, and the other one is the metal arc, more specified, and we use it twice in this part of the lab. And this is connected to the oscilloscope, where we basically measure or see the relation between voltage and retardance from the Axometrix program on the computer. You good? Okay, for setup number 2 was a bit different. We just started with the laser. We had two polarizers and the liquid crystal in between them, and a detector connected to a transimpedance amplifier into an ohm meter where we measure voltage. Again, we have a function generator driving the liquid crystal, and basically by adjusting the amplitude, we see a change in the voltage, which is connected to the oscilloscope. And basically in this part, we're basically comparing the RMS voltage and the voltage from the ohm meter.
Hi, my name is Stephen Hames. So what we have here is an LCC, and what it's doing is it's taking this incoming polarization, which is linear because we have a linear polarizer here, and it's rotating it. It's doing that by adding retardance, and then it will come out at a different angle, and then this linear polarizer will either block or pass a certain amount of that light, and then we'll detect it at the detector.
Yeah.
So these are the results, and we modified our peak-to-peak and RMS voltage, and as we did that, we can see different intensities. This one is for the LCC, the Boulder LCC crystal. We didn't get as good results for this one as the other one, but you can see that it is modulated a little bit depending on the output voltage of the function generator. And then we also rotated it. We set it to our max voltage, and then we rotated it. And as we rotated it, we see that changes it as well. We had to omit these points because the wire got in the way. It blocked the laser, but you can see that. Anyways, the metal arc gave us much cleaner results, if you will. And you can see how as we modulated the voltage, we get different intensities. And we went all the way to 10 for each one. And this also gave a very nice rotation graph. As we rotated it, we got a sinusoidal pattern, which is...
Alright, so I'm Brian Lacasse, and I was the layout design for this Lab 11. And so what we have here is we have our metal arc, and our function generator was used to drive this metal arc, so we apply voltage in a square wave fashion. And we didn't really see any change, and I can show you here if you want to look here. As it changed the voltage from about 10 volts to slowly down, you can see that there's not a whole lot of change in that green bar, which is the retardance. And additionally, the other information on the screen doesn't change much either. And so, for this portion of the lab, we didn't see what we expected at all because this information wasn't being cooperative, I guess. And so if you look on the oscilloscope here, I can prove that our voltage is changing. And so a few things we tried to do was switch out our cables just to see if any of the cables were causing the problem. We realigned everything, or attempted to, and we recalibrated everything. We actually were 0.7% out of this current calibration, and that was pretty good. That's all possible. So one other thing we tried is we put a linear polarizer in the system just to see if anything was going on. And as I rotate the linear polarizer, you can see that the polarizance and the attenuation along with the retardance all change. It's not really that significant, it just kind of shows that the program functions. So what we expected for this part was we expected our retardance to be inversely proportional to our voltage. So at low voltages, we expect a higher retardance, and as we increase the voltage, we would have expected it to fall off. We didn't see that. We only saw constant retardance, essentially. So we used a square wave for this section, and we also used it in the previous section. The reason we did this was if you apply a constant high voltage DC to these liquid crystals, you'll cause damage to them and they'll stop functioning. So what we do is we apply a fast AC circuit or AC power to them, and so this will have the same effect as applying a DC power, but it won't ruin the LCD or LCC.